So in this video, we're going to look at testing for concavity in the case where we have to deal with a function that doesn't have inflection points. So the example says determine the intervals on which f of x equals x squared plus 1 over x squared minus 1 is concave up or concave down. And here's the graph of f of x in the purpley blue color. And what we want to look at on this graph is we want to notice it doesn't look like there's any inflection points along here. It doesn't appear as though there's any there. It doesn't appear as though there's any there. If I look at the second derivative is positive, indicating the graph should be concave up. Here the second derivative is negative, indicating the graph should be concave down. And here the second derivative is positive, also indicating the graph should be concave up there. So I do have, it looks like 3 intervals over which the graph should be concave up. And the second derivative information kind of confirms that idea. So what we want to do is look at how we use calculus to make our determination for those intervals and identifying whether they're concave up or concave down. So the first step is to look at the graph of the function just like we've been doing and identify the domain of the function. And I want to look at this and say, hey, I have a rational function. So I know that the thing that could go wrong is that I could get a division by 0. So in fact, what we need is x squared minus 1 to not equal 0 so we don't get division by 0, which means we need x squared to not be 1, which means we need x squared to not equal plus or minus the square root of 1, which is just 1. In fact, that's why we see here we get vertical asymptotes at x equal -1 and x equal +1, exactly the functions that exactly the function values that f of x cannot take on. So the domain of f of x, based on these restrictions that x can't be plus or minus 1, the domain of f of x is going to be go from -infinity all the way up to the first vertical asymptote, union, jump over that vertical asymptote, start at the first vertical asymptote and run to the second one, the +1, union, jump over the second vertical asymptote and run from 1 to infinity. So step 1, identify the domain of the function because we combine the function domain with the inflection values of x to construct our test intervals. So once I've done that, I want to find the second derivative because if inflection points exist, then the second derivative is either going to equal 0 or it will be undefined. So start off with the original function. We have f of x equals x squared plus 1 over x squared minus 1. I have a rational function. It looks like I'm going to need to use the quotient rule to take this derivative. So the quotient rule says take the derivative of the numerator, which is 2x, and multiply it by the denominator, which is x squared minus 1. Minus, the quotient rule says take the derivative of the denominator, which is also 2x, and multiply that by the numerator, which is x squared plus 1. So we get x squared plus 1. And then the quotient rule says divide all of that mess by the square of the denominator. And then we want to simplify as much as we can. So I want to notice that 2x shows up in both terms. So I want to factor a 2x off, which will leave behind x squared minus 1, x squared minus 1, minus x squared by distribution, and minus plus 1 is minus 1. So I get x squared minus x squared is 0. I get minus 1 minus 1's minus 2. So in the numerator, I'm going to have a 2 times -2 when I simplify this, which is just -4. And that -4 will be times the x over the x squared minus 1. So there's my first derivative. To look for inflection points and to get the signs of our second derivative, we're going to need to calculate the second derivative. So we need to know f double prime of x, which is going to equal -4 times the derivative of this rational function. So again, I'm going to need to use the quotient rule again. So I'm going to get the derivative of x is 1 times the denominator using the quotient rule. So x squared minus 1 quantity squared minus the derivative of the denominator, which is going to be 2 times x squared minus 1. We have a composite function, so we need to use the chain rule. So then it's going to be times the inside function, which is twice x. That's the derivative of the denominator. And now we need to multiply that by the numerator, which is just x. And then it's going to be, this mess will be all over. Notice I didn't include the -4 in the numerator, or I'd have to have put a parentheses in. And then I need to square the denominator. So x squared minus 1 squared again is going to be to the 4th power. And now I want to continue to simplify. So when I look at this, I see that I have an x squared minus 1 term showing up twice in each of these two terms. So I can factor off an x squared minus 1, which will leave some stuff behind. Factoring it off with the first term here, x squared minus 1 factored off will leave an x squared minus 1. Minus, I'm factoring an x squared minus 1 off of here, which will leave behind a 2 times 2 is 4. X times x is x squared. And this will all be over x squared minus 1 to the 4th power. But this x squared minus 1 will cancel one of the 4 x squared minus 1s in the denominator. So this is going to equal, I can simplify some more. I have a -4 times, I have x squared minus 4x squared is minus 3x squared minus 1 in the numerator over. And I have x squared minus 1 cubed in the denominator. And it would usually be customary to factor a negative off of this and cancel it with the negative out here. So usually you would see this written as 4 times 3x squared plus 1 all over the x squared minus 1 quantity cubed. And there's our second derivative. So put a little box around it. So inflection points require one of two things to be true. Either the derivative needs to be equal to 0, which would mean the numerator of the derivative needs to equal 0 because I have a rational function here. So I would need 3x squared plus 1 to equal 0. And if we try to solve this, we're going to get x squared equals -1/3. So we would get x equals plus or minus the square root of -1/3. And this is a complex number, so there isn't a real number 0 for this derivative. So I don't need to worry about the derivative being equal to 0. So I want to note that the derivative can't be equal to 0 because 3x squared plus 1 cannot equal 0. So the other thing that can happen is the denominator could equal 0. In this case, the only way for the denominator to equal 0, which would cause an undefined derivative and an inflection point, would be for x squared minus 1 to equal 0. And this can happen because we would get this, and then we would get x equals plus or minus 1. But what I want to notice is that if the derivative is undefined, if we get a division by 0 in the denominator of the second derivative, that these values plus or minus 1 aren't included in the domain of f of x. So I'm not going to get an inflection point on f of x at the values plus or minus 1. So this is a case where if we try to determine where the derivative is undefined or equal to 0, we discover that there are no possible locations for an inflection point for our function f of x. And that corresponds to the graphical evidence that we see over here. So the idea is if there are no inflection points, and there aren't because 1, the numerator can't equal 0. 3x squared plus 1 cannot equal 0 unless you're willing to work with complex numbers. And 2, the values plus or minus 1 that zero out the denominator of the second derivative are not part of the domain of the original function. So because there are no inflection points, our test intervals, so there's no inflection points, our test intervals are just going to be correspond to the open intervals that describe the domain of the function. So the test intervals are just going to be negative infinity to negative 1, negative 1 to 1, and 1 to infinity. Our test intervals correspond directly to the function domain, which was the first thing that we identified in this process. And so now we need our test values that we plug into the second derivative to determine the sign. So I look at this first interval and I see that x equals negative 2 is in there. The second interval, I see that x equals 0 is in the interval from negative 1 to 1. And in the interval from 1 to infinity, I see that x equals 2 is in there. So we just plug those test values into our second derivative. So f double prime evaluated at negative 2 is going to equal, we'll get 4 times 3 times negative 2 squared plus 1 over x squared minus 1. So it's going to be negative 2 squared minus 1 all cubed. So if we simplify this, we're going to get 4 times negative 2 squared is 4 times 3 is 12 plus 1 is 13 over negative 2 squared is 4 minus 1 is 3. So we get a 3 cubed, which is just 27. And what I want to notice is I have a positive times a positive divided by a positive. So the second derivative at negative 2, the sign of it is positive. And if we're positive, then we know that the graph is going to be concave up on the test interval. So we conclude that our graph is concave up on the interval from negative infinity to 1. And now we have 0, x equals 0 as our next test value. So f double prime evaluated at 0 is going to equal 4 times 3 times 0 squared plus 1 all over 0 squared minus 1 all cubed, just plugging 0 into our second derivative. And if we crunch these numbers, we're going to get 4 times 3 times 0 squared is 0 plus 1 is 1 over 0 minus 1 cubed is going to be negative 1 cubed is negative 1 is just negative 4. So the second derivative evaluated at 0 is negative. So the sign of the second derivative on our test interval is negative, and we conclude that our graph must be concave down as a result, and that matches the graphical evidence that we have between negative 1 and 1. The graph is opening down or concave down, and our last value, test value, is x equal to 2. So f double prime evaluated at 2 is going to equal 4 times 3 times 2 squared plus 1 all over 2 squared minus 1 quantity cubed, which is just going to equal 4 times 3 times 2 squared. 2 squared is 4 times 3 is 12 plus 1 is 13 all over 4 minus 1 is 3 squared, or cubed, sorry, is 27. So without even crunching this anymore, I see I have a positive times a positive divided by a positive is a positive number. We conclude that the graph is concave up on the open interval from 1 to infinity. So now we need to draw our conclusions. We conclude that the graph is concave down when x is an element of. We were concave down only on the interval from negative 1 to 1, and we were concave up on 2 intervals, so we need the union of those intervals. So when x is an element of, the first interval on which we were concave up was the interval from negative infinity to negative 1. Union, the second interval on which we're concave up, was the interval from 1 to infinity. So we add that interval to the union, and there is our locations where we're concave up.